Good afternoon, everyone. I welcome you all to the sixth monthly HBNI alumni webinar. I welcome our uh, speaker, Dr. Shandip Joshi, Professor A.K. Tagi, Dean HBNI, and all the students and faculties offline and online and other participants to the webinar. This webinar series is designed to help the present students of HBNI in their placement and to connect with our alumni of HBNI. Thank you all for being a part of today's webinar. I will now invite Professor Tagi to give some remarks.
Very brief remarks. This series of webinar we started so as to integrate our alumni with the existing PhD students. I see number of them are sitting here and online also. In any university, alumni play a very big role. They can be full-time student, they can be our employee students like Sandeep. So it is very important exercise. I must compliment you for doing it regularly to engage them, because that's how we connect generations. This is a wonderful thing, and we facilitate the sharing of their experience with present generation students. And the topic which Sandeep has chosen, career prospects in quantum computing, I have been myself giving talks on career prospects in chemistry for last 25 years. And I know how popular they are, I know how useful they are. But now those talks are on traditional subject like chemistry, whereas this one is on cutting edge, upcoming field. And I know Government of India's quantum mission, in which 8,000 crore rupees have been sanctioned. And I know the kind of industry is going to come up. And I also know the kind of employment is going to come up out of this year, both in academia as well as industries. So no other topic could have been better in today's scenario. With this, I also welcome Sandeep.
So I first thank our esteemed, thank you, sir, for your inspiring words. I thank our esteemed alumni speaker, Dr. Sandeep Joshi, Scientific Officer, BRC, who has agreed to give a talk to our students. Dr. Sandeep Joshi joined Nuclear Physics Division, BRC, after graduating from 56th batch of training school in 2013. He has done his BSc and MSc degree in physics from Delhi University. Dr. Joshi completed his PhD from HBNI in 2021 in neutrino phenomenology and received CVK Baba Best Thesis Award from the IPA. During postdoc at Northwestern University, he worked on quantum computing with superconducting qubits. His current research focuses on optimal control of qubits and quantum simulation. Today's alumni webinar, Dr. Joshi will present on career prospect in quantum computing. I encourage you all the students to actively participate, ask questions and engage with our speaker and fellow alumni. Your contribution and perspective enrich the dialogue and enhance the overall experience for everyone involved. Without further ado, let us commence this webinar. Over to our alumni speaker, Dr. Shandip Joshi.
Yeah, so thank you, ma'am, and thank you, sir, for giving me this opportunity in this special webinar series. Even though I must admit that it was not an easy talk to prepare because the diverse background of the audience involved. So I've tried my best. I've tried to make it a bit more technical as well, especially for the people from the physics background. But if people who are from not from the physics background, if they have questions, then please feel free to interrupt and ask questions. Okay, so we'll start. Okay, full screen. I- No, I think the earlier one was good. Control L. This is where, okay. Okay, yeah. Okay, so let me first start. Okay, so let me first share this first slide, which is called Moore's Law for classical computing. So Gordon Moore in 1965 predicted this behavior of transistors in microchips, which is now known as Moore's Law. So you can see that in the early 1970s, the chips contained very few transistors, which is of the order of 1,000. And Moore predicted that the number of transistors on a given microchip will double every 2 years. And this trend has continued even till date, but now it has started to show some saturation because of some quantum effects as well as some limitations of techniques such as photolithography. And so, but this law has held up pretty well till now. And in quantum computing, we can plot a similar law, where now the number of transistors is replaced by the number of qubits. So qubits, what are qubits? I will explain later. So qubits are basically the fundamental unit through which we perform computing in the quantum domain. So in the quantum computing regime, you can see that this behavior is we are still in the initial layer, but behavior seems almost like an exponential behavior, especially for companies like IBM and D-Wave. So, but the number of qubits is not the only metric which predicts or which qualifies how good a quantum computer is. Other factor we have to consider is that the qubits that we currently have are noisy. So that's why it's called noisy intermediate scale quantum computing era, or NISQ era. So John Preskill coined this term, that not only the number of qubits is important, but also the quality of qubit. And why it's difficult to make good quality qubits? Because the quantum information that we have, which the quantum information processing is a very fragile process. As soon as we interact with our quantum system, it essentially amounts to disturbing the quantum system. So we want our qubits to be well isolated from the environment, but at the same time, we want to control the qubits. And also we want to couple the qubits together. So these are like two contrasting things that we have to do at the same time. We want our qubits to be isolated from the environment, as well as we want to strongly couple them to do control tasks, as well as couple them together. So that's why it's very, very difficult to make these quantum computers. And a lot of work has been gone into basically fabricating good quality qubits and enhancing the control capabilities on these qubits. So why quantum computing is important? So there are several reasons why people are interested in quantum computing. So one of the main reasons that people are interested is what is known as quantum speedup. So what is quantum speedup? So quantum speedup is achieved when a quantum computer solves a problem faster than any of the classical computer with best available hardware and running the best algorithm. And it has been, even though it's not possible to do all the tasks on a quantum computer faster than a classical computer, but there are certain tasks. For example, there is famous algorithm called Shor's algorithm for prime number factorization, which offers super polynomial speedup. That means if I increase the size of the input, then classically the time required for factorization of a prime number increases exponentially, while if the same while the same task on a quantum computer will give me a polynomial time scale. Similarly, there are algorithm which is called Grover's search algorithm, where we get polynomial speedup. So there are certain kind of tasks which a quantum computer can do better than a best available classical computer. The other reason we are interested in quantum computing is known as quantum supremacy. This is again a term coined by John Preskill. So quantum supremacy is basically the goal of demonstrating that a quantum computer can solve a problem that no classical computer can solve in any feasible amount of time. And this has been proved in a couple of experiments. The famous experiment being the Google's quantum supremacy experiment, where they basically showed that a task which a quantum computer solves in 200 seconds, that on a classical computer it will take thousands of years. So these are a couple of reasons. And the final reason, which is more fundamental why we are interested in quantum computing, is more fundamental, is because of quantum simulation of highly entangled states of matter. So for example, if we are interested in things like quantum spin liquids or high TC superconductivity, then Feynman predicted that the quantum computer will have clear advantage over the classical simulation. So with this, I'll just briefly outline my talk. So I will first introduce some basics of quantum computing and what are qubits, what are quantum gates that are required to perform quantum computing tasks. Next, I will introduce what are the kind of hardware on which we can implement quantum computing. At present, unlike classical computing where the technology is fixed, we have integrated circuits and transistors, quantum computing is still an evolving field, and there are multiple platforms which are competing for this quantum computing hardware. So different platforms will have different advantages and disadvantages. So I will discuss those things. And then I'll focus on what are the career roles and skills required if someone wants to perform. Okay. If someone wants to basically get involved in this field or contribute towards this field. And I'll briefly discuss what are academia and industry and how contrasting are it's to work in these two different fields. So in quantum computing, the basic unit is what we call a qubit. So just like classical bit can be in state 0 and 1, so basically we do all our classical computation using these binary codes which consist of series of 0 and 1. Qubit can also be in state 0 or 1. However, there is a property of qubit which is not there in classical regime, which is called superposition. For qubits, we can form superpositions of 0 and 1 as well. So a nice pictorial way is to represent this in a block sphere. So where we have, in addition to 0 and 1, we can form any arbitrary superposition of 0 and 1. However, when we measure a qubit, this state collapses to one of the states, 0 or 1. But during the quantum information processing, we can create any kind of superposition of 0 and 1. Another property in which quantum computing differs from classical computing is called entanglement. For example, if we have two qubits, we can form entangled state like the famous Bell state. And this state, it's not possible to create classically. And this state is such that the measurement correlations are stronger than could ever exist between classical systems, a theorem which is known as Bell's inequality. So the property of superposition and entanglement for quantum computers is what basically gives the power of quantum speedups to quantum computers. So how do we basically do quantum information processing? So essentially we have a two-level system, just like I showed before, a two-level system which consists of, let's say, a ground state and an excited state. And these two states form a computational subspace. So this is basically our qubit. And if you want to create multiple qubits, basically entangle multiple qubits, then we can couple them through various channels. For example, here I have shown this in a very abstract way. So the Hilbert space dimension of n coupled qubits scales like 2 to the power n, because each of the qubits has two levels. And when we do quantum information processing, just like classical information processing, we can perform gates, various gates, gate sets on these coupled qubits. For example, X gate, Y gate, Hadamard gate, or 2-qubit gates. And there is a concept called universal quantum computing, basically, which says that if we have a set of gate is said to be universal for quantum computation, if any unitary operation can be approximated by a circuit involving those gates. So basically, what we need is a set of single qubit gates as well as an entangling 2-qubit gates. That means we can perform any task that a classical computer can perform on a quantum computer if we have a set of single qubits gates as well as at least one entangling 2-qubit gate. So this is known as DiVincenzo criteria for universal quantum computing. So if you have any question, then please ask. So this part was a little bit technical, especially for the non-physics audience. So please ask questions if you have. Okay, so yeah.
Fiducial state.
Sorry.
Simple fiducial state.
Okay.
Can you hear me?
Yeah.
I wanted to know about the simple fiducial state.
So basically, whenever we perform any algorithm, after the algorithm is done, we want our basically quantum processing unit to reset to its initial state. So basically, in most cases, it's the ground state of the system. So we want to basically reset the state. We have to have the ability to reset our quantum computer to ground state. So this is the simplest possible state that we can have.
Excuse me.
Yeah.
Different gates you generate,
Mhm.
that also includes this entangled state also.
Yeah, so we can create gates. For example, here I show this C0 gate. So this C0 gate, the way it works is that the first qubit is the control qubit and the second qubit is the target qubit. So if my control qubit is in ground state, it doesn't do anything to the target qubit. But if my control qubit is in excited state, ket1, then basically it flips my target qubit. This is called C0 gate. And using this gate, we can generate entangled state like Bell states. Yes. In?
Of these gates, combination of gates.
Uh-huh.
Pauli X gate, then you have Hadamard gate.
Mhm.
So if you give some inputs, what is the output? Can you simulate in
Yeah, this can be easily simulated. Yes.
which platform?
So there are platforms like IBM Quantum has an online platform where you can simulate this kind of behavior. So, but also you can do using quantum simulators like Qiskit.
Yes.
Yeah. So this can be done. Yeah. And there are basically softwares called QTIP where you can do these kind of simulations.
Can you show some example that you have given some gates and this is the output is coming?
Yeah. Oh, that I have not because.
First presentation
Ah,
and then questions.
okay.
It will be more coherent. Please do ask here.
Okay. Yeah. Okay. Sorry. Okay. Yeah. So how do you basically implement this quantum computing on an actual hardware? So there are, as I said, multiple platforms available for this. For example, I have listed some of the famous platforms. For one of the famous platform is called trapped ions. So in trapped ions, basically what we have is ion traps by ions which are basically charged particles which are trapped electromagnetically, and the energy level of the trapped ions form qubits. The advantage of trapped ions technology is that they have really long coherence time. But the problem lies in the scalability. How do you scale to higher number of qubits? That is one of the challenges. So far, I think trapped ion technology has reached around 18 to 20 qubits as far as I know. But scalability and control is one of the issues in TrapDance. Another platform which is also quite popular is called cold atoms or neutral atoms. So here, because the atoms are neutral, we cannot use electromagnetic waves, but these atoms can be trapped by what are called laser tweezers or optical tweezers. And again, here the energy levels of the atoms, because they are highly enharmonic, they can be used to form qubits. Again, here the coherence times are very large. That means you can preserve the quantum information for long time, but the scalability is hard. One of the most famous technologies called superconducting qubits, which I'll come to later. But there are other exotic technologies like Majorana fermions, which are based on topological effects, or photonic qubits, which are also called flying qubits. So in the end, right now we do not know which technology will end up as emerge, which technology basically will be there in, let's say, next 20 years. But it is quite possible that a combination of technologies or combination of physical platforms will be used for performing different tasks. For example, photons can be very useful for quantum communications, and superconducting qubits can be very useful for having scalable quantum computers. Currently, there are multiple companies which are various companies which are also involved in developing this quantum computing hardware. For example, in superconducting qubits, we have Google and IBM Q and Rigetti. For TrapDance, we have IonQ, which basically demonstrated this 20 qubit processor. And similarly, for neutral atoms or silicon dots, we have different companies which are also involved in developing the quantum hardware. Okay, so let me tell briefly about superconducting circuits, because this is the field where I work. So superconducting circuits are based on essentially on Josephson junctions. So what are Josephson junctions? So Josephson junctions are kind of tunnel junctions which are made of superconducting materials. So we have two superconducting materials which are separated by a thin insulator. And when they are cooled to very low temperature, there is Cooper pair which tunnel across this barrier, and it essentially acts like a nonlinear inductor. And this nonlinear inductance is the property which basically is crucial for making these qubits. And these Josephson junction can be fabricated on a 2D chip, and they can be embedded on a 2D planar resonator as well as 3D resonators to form a setup which is called a circuit QED, where we perform all the gates and do all the quantum control tasks. And the advantage of superconducting qubits is that we can use them as artificial atom. That means we can design them according to our needs. For example, if we want a higher enharmonicity qubit, we can create a fluxonium type of device. If we want a scalable type of arrangement, we can form what is called an XMON. If you want a qubit with very large coherence time, then we can again form these 0-pi qubits. So depending on our requirement, we can form different types of qubits. That's why they are popularly known as artificial atoms. So this is what a typical qubit chip looks like, for example. So here you can see that there are multiple qubits which are connected through these resonators. And these yellow dots, you see these are qubits. So it's a 7-qubit chip. So, and we can control these qubits using these charge lines. These pink lines are called charge lines, as well as we can flux bias them through these flux lines. And also, we have to have the ability to read out these qubits. That's why we need these readout resonators or feed lines. So this is how a typical qubit chip looks like. Basically, if you want to implement any gate, we basically put some microwave pulses through these charge lines and flux lines, and we can couple these qubits through these resonators as well as do the readout. And And this is how a fully assembled QPU looks like from the outside. So this is from the IBM Q. So this is the outer shield, which is at room temperature, and inside this we have this golden chandelier which is hanging from the top. And so this is called a dilution refrigerator. We need to go to really low temperatures, like of the order of 10 to 20 millikelvin, in order to basically isolate this qubit chips from the thermal noise. And this dilution refrigerator has multiple stages at 4 Kelvin, 1 Kelvin, and then base Kelvin of around 20 millikelvin. And these input lines basically connect the room temperature to these qubit chips, through which we can send control signals. And these output lines basically gives the readout signal. Through these output lines, we can read out the state of the qubit. So this is how a typical dilution refrigerator or a QPU looks like from the inside. QPU is basically a quantum processing unit. So this can contain 1 qubit or a multiple qubits. So from this introduction, I think now you may have idea that this is a highly interdisciplinary field which requires which can have multiple career options. So, for example, there are opportunities from people who are from physics background, math background, computer science, electrical engineering. For example, a person who has done mechanical engineering, he can work, if he has experience with cryogenics or RF measurements, he can contribute to this field. Person who is from computer science background, he can contribute through software development or through writing the code, which do quantum control codes. And people, of course, from physics background, they can do microfabrication. Or people who have experience with microfabrication or nanofabrication, they can also contribute to this field. So there are various multiple career roles which are available in this field, especially in superconducting qubits and in general in other platforms as well. So, for example, if someone, how do I get started in this field? So this is some basic recommendations. So one can start with some simple books. So for example, this book called Nielsen and Chuang, Quantum Computation and Quantum Information. This is, even though it's a bit outdated, but it's known as the Bible in this field. So one can start reading this book. There are very good lecture notes by John Preskill on quantum computation and information. And there is another very good book called Exploring the Quantum by Serge Haroche, who is a Nobel laureate, and James Ramo. So these are some of the popular books where one can learn some of the basics in this field. There are many online resources. For example, there is a YouTube channel called Qiskit, which contains some very good introductory lectures as well as some technical lectures which one can follow. There is another very interesting YouTube channel called Introduction to Quantum Computing, which contains some very introductory stuff. So this is mainly focused from the point of view of superconducting qubits, but it contains some very introductory stuff on quantum computing as well. As well as there are online forums like Coursera or MIT Open Courseware, where one can do some courses and get started in this field. There are multiple conferences which are of introductory nature, where there are workshops, people organize workshops, which basically contains some very introductory stuff. For example, there's an IEEE International Conference. It happens every year. I think it's in US, I'm not sure, but mostly it happens in US. So one can attend these type of workshops. There is US QIS. I have the opportunity to attend the inaugural school of this US QIS, and it contains some very good lectures. And there is also a Qiskit Summer School, which is an online school, so you don't need to go anywhere, which you can attend from your home. So this happens every summer, I think. What are the other opportunities? For example, if people who are already slightly experienced, people who have experience with microfabrication, or people who have experience in low temperature physics or RF technology, they can apply for postdocs and fellowship. There is very good online there are very good online platform. For example, Academic Jobs Online, which I think every graduate student knows. They have they have a lot of options on quantum computing jobs and as well as postdocs. So typically the applications start around October, November every year. So you can go there and apply. And there are jobs, there is job section in magazines like Physics Today or Physics World where you can go and search for jobs. There are websites like Rumor Mills, condensed matter rumor mills, or high energy physics rumor mills where you can look for job opportunities as well as.
Interesting name, Rumor Mills.
Yeah, it's a very interesting.
What was the reason that this kind of name was chosen? Attractive or just catchy?
No, it's not catchy. Actually, it started way back where so it started not for postdoc application but for faculty position. So in US basically what happens is that whenever a faculty position is announced, there are rumors that who will be shortlisted and who will be given the position. So so I think that's how the name started. And now it has been extended for postdoc positions also. And another popular way in which you can, especially this is popular in the European context, is you can directly talk to the PI and write grant applications with the PI. And you can sign up for newsletters. For example, if you're interested in quantum news, there is newsletter by Oak Ridge National Lab. There are newsletters by Quantum Computing Reports. So you can just go to these websites and put in your email, and then every week they will send you some emails regarding what is happening in this field and what are the current trends. And finally, I would like to basically compare how it's like to work in academia versus how it's like to work in industry. Even though I have never worked in industry, so it's just an outsider's perspective. So in academia, when we work or in any research center or university, the focus is on novel inventions and pushing the scientific boundary. For example, people want to develop qubits with higher coherence time, just like the 0-pi qubit I showed above. Or people are interested in designing better error correction protocols or better techniques, better control techniques. Whereas in industry, the focus is more on product development and the scalability aspect. For example, IBM just announced, I think last year announced a qubit chip with more than 1,000 qubits. So there the focus is more on the scalability and the product development aspect of it. There are companies which provides dilution refrigerators. For example, Blue Force, Layden, or Cryoconcept. So these are the companies which will provide you with the hardware setup. There are companies, in fact, we are in talk with one of the companies called Quantware, which specializes in providing the specialized quantum chips or readout hardwares. So in academia and industry, the focus is slightly different. And in academia, while you have the individual responsibility that you want to publish, but you also have longer timelines because the problems are really challenging, so you get longer timelines. In industry, the focus is more on teamwork, and you certainly have higher deadlines because ultimately you have to come up with product, and company has to focus on profitability as well. And as we all know, in academia, the budgets are tighter, the remuneration are smaller, while in industry, the salaries are obviously higher. So whenever you want to choose, you have to basically weigh these options also, where you want to work, whether in academia or industry. The opportunities are plenty in both academia as well as industry. So yeah, so with this, I think I would like to summarize my talk. So quantum computer is a rapidly growing field with opportunities in both industry as well as academia. It is, as I said, interdisciplinary with diverse career roles from physics to engineering, as well as material science. And if you are new to this field or you want to enter this field, I think one should focus on imparting oneself with new skills or educating yourself. And then I think there are plenty of opportunities if you are interested in this field. So yeah, so with this, I would like to thank you.
Thank you very much, Dr. Sandip Joshi. And now it is open for question. So, people here online, offline, please introduce yourself and ask question. Okay. I can use the mic.
Explain something about the quantum Fourier transform, how it differs from ordinary Fourier transform.
What is a quantum Fourier transform? See, quantum Fourier transform. So, for example, a Shor's algorithm, which I showed above.
Sure.
So that essentially,
Basically, how it differs.
how it differs from, yeah, I don't think I have a good answer to that, but quantum Fourier transform, essentially, we are going from the space of, we are essentially going to the space of frequency space of the qubits, right? Using quantum Fourier transform. Just like in normal Fourier transform, we go from normal space to frequency space. Similarly, time domain to the frequency domain. Similarly, in quantum Fourier transform, we go from usual Hilbert space to the frequency space of the qubits. And I don't have a simple enough answer to explain that without showing you any example. For example, it is essential for any, for example, Shor's algorithm crucially depends on quantum Fourier transform.
I give you some circuits, but gates. How can you simulate? Let's say gate is there, and we are applying on C0 gate, on Hadamard gate. So how the inputs are changing and outputs, how we can simulate?
So basically, in superconducting platform, what we do is we have a qubit, we have Josephson junction, and we have RF lines connected to those Josephson junctions. And if you want to implement, let's say, an X gate, we will give an RF signal corresponding to that gate. And that will implement an X gate on our qubit. Similarly, for C0 gate, we will give a different type of RF signal. So the quantum, how do we control the qubit, that becomes important.
And mathematically, how will you simulate?
Mathematically, it's
0-1 combination I'm giving.
uh-huh.
You simulate quickly.
Yeah, of course. You just need an X gate. You need the pulse level simulation or just the
Mathematically.
mathematically it's just an X gate. So basically, what an X gate does, it converts a ground state to an excited state or an excited state to a ground state. So mathematically, you can simply use platforms like Q-tip or Qiskit that will simply do the job for you. But if you want to do the pulse level simulation, that is also possible for superconducting qubits.
Anybody from here, you want to ask question? Introduce yourself.
Yes, I'm Gaurav Mukherjee from Nuclear Physics Division, BRC. I wanted to learn more about the scalability issues for the different hardwares and
Scalability. Yeah, because can we slide number? This one. I think this one. So for example, consider the case of trapped ions. So in trapped ions, what we do is basically we are trapping these electromagnetic ions, these charged ions through electromagnetic fields, right? So how do you scale the qubit? Essentially, you have to couple the qubits. And to couple the qubits, you have to have certain level of controllability. So with trapped ions, it's not such an easy thing because you have this cloud of ions in which you have to basically, if you want to couple one ion to the other, you have to apply certain type of electromagnetic field. And to generate that configuration may not be such an easy task. Whereas in superconducting qubits, because the qubits are fixed on chip, so you can easily connect them through resonators, easily couple them through capacitively or inductively. So the scalability becomes much simpler in case of superconducting circuits because everything is on chip.
so in the ions you have the nuclei with a few electrons around.
Yeah, it's basically an ion. It's a charged ion.
Okay.
It's basically a cloud of ions. It's not one ion.
Okay. And for the cold atoms, they're neutral atoms but cold.
They are at low temperature, so they are neutral, so you cannot trap them electromagnetically. So you need something called optical tweezers. They are based on laser technology, and you trap them using those tweezers. And there are basically you have to excite them to certain level, higher states. So they are called Rydberg atoms, Rydberg states, and using those you form the qubits.
Okay. It may be possible in principle to have other systems also, like for usage as qubits.
Yeah. Any two-level system basically that you can create on a physical platform can qualify as a qubit, provided you have to have the control as well as the scalability.
Thank you.
You worked during your post
Superconducting qubits.
superconducting. So as an user, suppose somebody is doing just numerical solving some equation for classically to make it quantum for the quantum computer using that and solving. What are the steps and how one has to go? Because all algorithm has to be changed.
Yeah.
Compiler. It's a new concept totally. So different. So where we are now?
So it's not actually, it's not even advisable to solve each and everything using a quantum computer, because quantum computer is a very specialized machine.
Yeah.
And it runs on entirely different physical principles. So there are certain type of tasks in which quantum computer has advantage, but I think for normal day-to-day processing, classical computing is sufficient. But for example, if you want to simulate really highly entangled states of matter, for example, spin liquids, then classical computer may have limitations. There you may use specialized algorithm for quantum computing. But for normal day-to-day purposes, I think.
No, it's not the purpose that which you can solve even in a year to move to that, but some kind of other problem which is some large-scale simulation which takes whether we can move to quantum computing. That's my
of
point.
course, people are trying that. For example, that's why first thing is we need good quality qubits. Right now we are in the era which is called NISQ era, noisy intermediate scale.
Yeah,
That
that's
means-
another point. You were mentioning that there will be a lot of noise. What kind of software people are working on to cut down that noise?
No, so it's not a software issue, it's a hardware issue.
That's so.
Yeah, because the quantum information is so fragile, whichever platform you use, whenever you interact with the quantum system, you end up disturbing that. So you don't want that. But at the same time, you want to control the system. If you want to run the quantum algorithm, you want to control those qubits as well as couple them strongly with each other. So these are two contrasting things which you have to do it simultaneously. So that is where the main challenge lies.
Any question from online? Or anybody?
So, extending is the same question what Mathis have asked. Okay. See, for example, I'm from engineering background. Okay. And if I look at typically, once you are also highlighted in that slide also, that this is the environmental simulation, for example. Domain is huge. For example, you want to simulate some cyclone or something like that. Okay. So physical domain is very huge. Okay. And typically, if you look at the traditional methods, they fail. What is being done is something like lumping sort of thing somewhere, and that is how we are doing today. What is the scope for this quantum computing there? And how, means if you contemplate today, what is the typical time frame we can expect based on your judgment? Nobody can predict accurately. I can say that typically this is the time you will be able to realize this sort of computing using quantum computing.
You mean like simulation of a cyclone, for example?
Right. We are doing today also.
Yeah.
Okay.
So
For example, if you look at turbulence modeling, what is that? Typically, in turbulence modeling, also what we do is, if you look at typically the scale of the eddies and the time frame, at the rate at which they are being formed and they are being destroyed. Typically, that runs into something like 10 to the minus microsecond, if time scale is. And if you look at again size also, that is also very small because the origin is very small. So typically, since we cannot resolve them, how we are doing is at engineering scale today is we just want to capture their effect, and we are doing something sort of you can say large eddy simulations. Micro scale, it is somewhere heuristically it is being modeled, somewhere using empirical correlation, somewhere like that. But if you look at the DNS, direct numerical simulations, there simply if the moment I go for something like Reynolds number greater than 10 to the power 5, which is typically the turbulence is highly turbulent, is Reynolds number is much larger. There itself, Jana, we cannot use these direct numerical simulations.
Okay.
That is what people say that somewhere. I just want to know, understand that how we can use the.
I think.
And another question is the way you showed the first slide. Let's see, it is like this, gentlemen. So okay, you were having this initially vacuum tubes, and then you have progressed the integration of the circuits. Because today, how we are able to do? Because in handheld, I am an entire computer itself. Okay, having much more versatile power than what they were initially, typically. What is the time scale, or what is the integration?
I think I will answer the second question first. So with quantum computer, as far as my understanding is concerned, it's always going to be a special purpose machine. It's not going to be a machine which, for example, you can carry in your hand because you require certain special type of algorithm and certain special type of training to actually operate those machines. So you cannot expect them to carry in your hand.
Other thing is maybe environmental conditions also, because
Yeah,
the
of
way
course.
you are telling that this is superconducting material is there.
Yeah, of course,
Temperatures
you
are
need
low.
really low temperature. There are platforms which do room temperature superconducting quantum computing as well, but they are still in very nascent stage. So how it will pan out in next 10, 20, 30 years, it's very hard to predict. So at the moment, what people expect is that for different type of task, you will have different kind of platforms. For example, if you want to do some quantum communication stuff, then photonic computing is the best. If you want to do some scalable quantum computing, or you want to run some large scale simulation, do some drug simulations in chemistry, etc., then superconducting qubits might be important. So for different tasks, I think in the end, different physical platforms will be important. And about turbulence, I'm not sure how people will develop algorithms to simulate those kind of things.
One of your slides that there was mentioning somewhere. I can see that in this slide itself, somewhere it was there that. Metrology and computing.
No, this is metrology. This is not meteorology. This is metrology, means like measurement, quantum measurements. Yeah, quantum measurements. Yeah, metrology is just whenever you are doing quantum things, so you are basically doing quantum readouts. So right now, I think people have done communication of the order of few kilometers, but I'm not sure. Uh, okay. I'm not sure, but right now, so basically, quantum communication means you have to have some sort of entangled photons. And to preserve entanglement over that long distance, I'm not sure how they are doing it. But I mean, I haven't seen. Yeah. Okay. Okay. Okay, okay. Maybe I am not aware of that.
Observation. Just I want to share with you, Dr. Sandeep, again. See, when we were there in maybe Methida and they were matlab, quite senior to me, when these computers were introduced to us in the school first time, I was in 8th, 9th. Okay. And the first thing which was taught to us is how to calculate the profit, how to calculate loss and this, that. Then the thing which were told to us at that time, it was being told that, okay, this is not for the calculating this. This is just an example which is being shown to you. These devices are basically for doing highly scientific calculation at this time. But today if you look at
Yeah.
down the line, everything is being done using computers. It has penetrated to your this most important use is it is there in every shopping mall, every departmental store, and behind it is being run. So again, means my guess is that though the technology is there, but in future who knows? Once the technology becomes mature, where it is going to penetrate. But
Yeah, of
initially it is always the niche area.
Yeah.
Target is like that only because cost doesn't justify. Today the cost is so high. That's why we say only highly scientific jobs are which require really yes, it will be applied to that only.
Design is if it is hardware the main problem.
Yes, that's why we cannot make it.
The
We
same
cannot-
thing happened to them.
Yes, but in future, but sir, same thing was there. If you
In
look at all the other this electronic
Anti-system,
devices
big
also.
anti-system and
See,
then
the noise which you talked about, that noise was there also. Electromagnetic interference was the biggest noise. And then only then this insulated cables and
Yeah,
all
of
the
course.
everything came.
If there are development like room temperature superconductors, with that development, of course, you will have.
Difficult to say, man. My God. Yes, true. Look that. It's having much more higher. सर आपने तो मतलब में वो पंचिंग कार्ड वाला ऑपरेट किया है एटलीस्ट वी आर नॉट हैविंग दैट पंचिंग कार्ड हाँ हाँ पंचिंग वी आर हैविंग यस हाँ इस वजह हमने 386 से चालू किया था सर नेक्स्ट
and that time also it is 200 MB
Maximum,
maximum.
yes.
And that also we have divided into Linux and DOS.
DOS.
200 MB, 100 MB, 100 MB, and then we are doing that
प्रोग्रेस इज फिनोमेनल
same thing. All so now we cannot think of that. Okay.
But once again, sir, one request I want to make to
Same thing
madam.
is that
One request is there. So today's this lecture was more for the students and from the career perspectives. But we can have another technical lecture also for the beginners and for this. So you are nice enough and kind enough again, Janamis, let me tell you, that to cover some of the basics about that. But if you can elaborate more on that,
Yeah, of course.
that would be really means exciting for many.
And that's why I told because this field
Yes.
is new, so he has at least
Right,
some
right.
basics.
Because I don't expect.
And otherwise, people
Yes.
will not understand what is qubit.
Because if you, even if you can stimulate the thinking of only a few, I know, I'm sure everybody is not interested, everybody will not be pursuing. But those few,
Yeah, of course.
job is done. So that's why what I request you is through madam that we can have a lecture on this.
Yeah, of course.
Thank you, Sandeep.
Thank you.
It was really nice. Yes, madam, want to say something?
No question from online. Okay, there is no question. Any question from here? Any students?
Yeah, please.
This for the Majorana one, there is no metrology. For all others, there is metrology.
Uh,
Why is that?
yeah, I think it's still not realizable as far as I know.
Okay, okay,
Still a conceptual thing.
okay.
Okay, if there are no more questions, I have one question that how the industry here in India is now in this job, means in quantum computing, is how it is working.
India, I think still industry is not a big part in quantum computing. Still the research is being done in the labs. in universities and institutes.
Not in industry.
No, I'm not aware of any industry.
And job-wise, you find that mostly postdocs, or you are in outside in US or which countries?
Outside there are a lot of postdoc opportunities for sure.
But industry also.
Industry also, but industry requires slightly more experienced people, I think.
So for
Yeah,
Indian
I mean-
people, those who are doing only postdoc in maybe not in industry or any experience.
Yeah, I
they-
mean, if you have, for example, worked with RF technology or
Okay.
have experience in low temperature physics
Then
or
they are-
nanofabrication, then there are a lot of opportunities in industry also.
Okay. So with this, we thank you very much for your Dr. Joshi, and thank you to all who are present here in person, and thanks to all online participants. I am sure that YouTube talk will be going to be viewed afterwards by students who could not participate and get benefited. Thanks to IT person for making this online talk possible. Thanks to all. Thank you.